Back in 2019, humanity captured the very first photograph of a black hole. The subject was M87, a supermassive black hole with a mass 6.5 billion times that of our Sun, located at the heart of a galaxy some 55 million light-years from Earth. That original image was fuzzy, tinted orange, and far from complete. Still, it did something enormous. It proved that the most extreme object we know of in the universe was real, and that it looked pretty much the way physics predicted it would. Now the James Webb Space Telescope has trained its eyes on M87 again, and this time the results are stranger than anyone expected. The infrared images, published in September 2025 after Webb aimed its most sensitive instruments at the black hole back in June 2024, revealed something the existing models never predicted and that scientists still can't fully explain: a second jet shooting out in the opposite direction. It's faint, it's fast, and up until now, it's been completely invisible. This counterjet is racing away from us at nearly the speed of light, dragging material off in a direction we'd never actually observed before. We can only see it now because Webb's infrared cameras are able to cut through 55 million light-years worth of blinding starlight in a way no telescope before it could manage. Turns out the universe's most famous black hole has been quietly hiding something right behind it this whole time. And the closer Webb looks, the weirder things get. M87 isn't your typical black hole. Most supermassive black holes just sit at the centers of their galaxies, feeding slowly and giving off fairly modest amounts of radiation. M87 breaks that mold in nearly every way. With 6.5 billion solar masses packed in, it's one of the heaviest black holes we've ever confirmed. To put that in perspective, Sagittarius A star, the black hole at the center of our own Milky Way, weighs in at roughly 4 million solar masses. That means M87's black hole outweighs ours by more than 1,000 times. But sheer mass isn't the only reason astronomers have been obsessed with this object for over 100 years. It's the jet. Shooting out from M87's core is a stream of charged particles that stretches several thousand light-years, traveling at speeds that come close to the speed of light. That jet was actually first spotted way back in 1918 when astronomer Heber Curtis noticed a strange, straight ray of light coming from the galaxy's center in his photographic plates. At the time, he had no clue what he was seeing. It took decades of research before astronomers pieced together that Curtis had photographed material being flung out at near light speed by the magnetic fields surrounding an active supermassive black hole. This jet isn't some abstract concept or simplified illustration, it's a real physical structure. A glowing column of plasma stretching thousands of light-years into space, powerful enough to influence gas clouds and star formation throughout the galaxy and well beyond it. And until Webb's infrared observations last year, we'd only ever managed to see one half of it. Here's the thing about black holes that launch jets. The laws of physics, specifically conservation of momentum, and the mechanics of magnetic field acceleration demand that material gets shot out in both directions at once. One jet points toward us, and its twin, the counterjet, points away. The jet aimed our way appears bright thanks to something called relativistic beaming. When an object moves towards you at close to light speed, the light it emits gets compressed and intensified, making it look far brighter than it actually is. The counterjet suffers the opposite fate. Moving away from us, its light gets dimmed and stretched out until it practically vanishes into the background. Astronomers have long suspected this counterjet had to exist, but they simply couldn't pick it out from the galaxy's overwhelming glow using visible light or radio telescopes. That changed with Webb's near-infrared camera. By photographing M87 across 4 different infrared wavelengths and then digitally stripping away the galaxy's starlight, essentially clearing out 55 million years worth of stellar haze to isolate the jet itself, researchers were finally able to spot, for the first time ever in infrared, a counterjet stretching roughly 6,000 light-years out in the opposite direction. And that wasn't the only surprise. The main jet itself showed off details nobody had seen before. Twisting helical lanes spiraling through the plasma, distinct bright knots marking spots where particles get kicked up to extremely high energies, and a feature known as HST1 sitting close to the black hole, which turned out to be made of two separate substructures with different physical properties. That last detail suggests the particle acceleration process is far messier and more varied across space than earlier models assumed. This jet isn't a smooth, uniform tube of plasma. It has real internal structure and geometry. And now that we can actually see that geometry in infrared, explaining how a black hole builds and maintains a jet this intricate at this scale across this kind of distance just got a lot harder. So what does all this mean for our understanding of black holes? The 2019 image confirmed that M87's black hole was real. Webb's 2025 infrared observations confirmed something else entirely. That whatever this black hole is doing with the material falling into it is far more organized and far more violent than our current models can fully explain. Separately from these jet observations, another paper published earlier in 2025 revealed something that completely reshapes our picture of this black hole. M87's black hole is spinning at roughly 80% of the theoretical maximum rotation speed possible for any black hole. That upper limit, known as the Kerr limit, is the point at which a black hole's event horizon would technically be spinning at the speed of light, an absolute physical ceiling. Spinning at 80% of that limit means M87's black hole isn't just enormous, it's also an incredibly fast rotating engine, carrying an amount of angular momentum that's almost impossible to put into everyday terms. And rotation changes everything about how a black hole behaves. A spinning black hole actually drags the fabric of space-time along with it, a phenomenon known as frame dragging, or the lens-Thirring effect, which warps the geometry of space around it in ways a non-spinning black hole simply can't. Scientists believe this frame-dragging effect is the main force keeping the jet tightly focused, preventing thousands of light-years worth of plasma from just scattering in every direction. There's a direct link between how fast the black hole spins and how the jet behaves. The faster the spin, the more rotational energy it can pull from the surrounding space-time and pump into the jet. At 80% of the Kerr limit, M87's black hole has been feeding an enormous amount of rotational energy into this jet continuously, over timescales longer than our entire solar system has existed. That helps explain the helical structures Webb picked up in the jet. They're essentially a visible signature of frame dragging, with magnetic field lines twisting around the rotation axis as the spinning space-time drags them along, stamping that spiral pattern onto the plasma flowing through them. In other words, the jet isn't just coming from the black hole, it's actually recording the black hole's spin in its own structure. Every twist in those helical lanes that Webb captured is essentially a physical record of exactly how fast M87's black hole is rotating. Now, here's what Webb's observations haven't answered, because this is exactly where the real science gets tricky. Nobody fully understands the precise mechanism by which particles go from sitting still to rocketing along at 99% of light speed. The leading theory points to the magnetic field structure surrounding the black hole's ergosphere, the region of twisted space-time just outside the event horizon, pulling out rotational energy through what's called the Blandford-Znajek mechanism. It's a solid theory on paper, but we still don't have observational proof detailed enough to fully confirm it. The internal structure Webb spotted in HST1, the especially energetic region near the black hole's core, contains two distinct substructures with different spectral signatures that don't neatly fit any current model of particle acceleration. Something's clearly happening close to the black hole that our models simply don't account for yet. And as for that counterjet, now photographed in infrared for the very first time, it's racing away from us at nearly light speed, which means we'll likely never get data from it as detailed as what we have from the main jet. It's faint, stretched thin, and tough to resolve even with Webb's capabilities. What it might reveal about the symmetry of the jet launching process, if we could ever study it as clearly as the approaching jet, remains one of the big open questions that future telescopes will need to be built to tackle. M87's black hole has now been under observation for well over a century. It was the very first black hole ever photographed, and it's since been imaged by the most powerful infrared telescope humanity has ever built. And the more precisely we study it, the more precisely we're able to define exactly what we still don't understand. That first photo back in 2019 gave us a blurry ring of light wrapped around a dark shadow. It confirmed a theoretical prediction, it earned a Nobel Prize, and it settled the question of whether supermassive black holes actually look the way theory said they should. Webb's 2024 observations tackled a completely different kind of question, not whether the black hole exists or looks the way we expected, but what it's actually doing and just how complicated that process really is once you look closely enough with infrared. A counterjet that stayed hidden for 100 years finally photographed. Spiraling internal structures that trace the rotation of a black hole spinning at 80% of the absolute maximum. Acceleration mechanisms that come close to, but still don't fully match, our best theoretical predictions. A jet that's been blasting out material for longer than Earth itself has existed, stretching thousands of light years into intergalactic space, structured in ways that blurry orange image from 2019 never could have hinted at. This famous black hole has been sitting there, 55 million light years away, doing all of this for roughly as long as our solar system has been around. We've had telescopes pointed at it for more than 100 years now, and in 2025, we're still finding surprises in the data that nobody saw coming. That's the honest truth about where our understanding of black holes actually stands. This isn't a solved problem or settled science. It's a phenomenon that keeps revealing new layers of complexity every single time we build a better instrument and take a closer look at something we thought we already understood. It might be the most extreme object in the known universe, and we're really only just starting to scratch the surface of what it's doing. Don't forget to like, share, and subscribe to Nature Mystery Unravel Mysteries. Learn untold tales of history and stay in the exciting world of new discoveries.